This is the beginning of our discussion of significant figures. Sometimes significant figures are also called significant digits. This refers to a set of rules used by scientists to ensure consistency among results. So significant figures are really just there so that if someone in one place makes a measurement and someone else in another place makes a similar measurement, that we'll get the same answer. Or if someone does a calculation in one place, in another place we'll get the same answer when we do the calculations. So let's begin talking about the rules. So our first rule is that all non-zero digits are considered to be significant. I'm going to use arrows to indicate when a digit is significant. In the case of 1234, all of them are significant, and so this gives us 4 significant figures. The number 498 also has no zeros. Zeros are the first number that we get that are going to be somewhat problematic for us because sometimes they're significant and other times they're not. So this one has 3 significant figures. 176.55 has a decimal and some numbers after the decimal, but that doesn't affect whether non-zero digits are significant or not. So in this case, we have 5 significant figures. Our second rule is the first rule that discusses zeros. And if we look at the first example, 109, rule number 1 tells me that the 1 and the 9 are significant. So now the 0 is the question. If a 0 is in between other significant digits, that 0 is considered to be significant. It would be a situation, something like a measurement is made and a 0 happened to be in the middle of the measurement, or a calculation is made and the calculation generates a 0 in the middle of the calculation. So this one has 3 significant digits. Our next one has the 4, the 9, and the 7 that are automatic. The 0 between the 4 and the 9 is in between significant digits, so it is also significant. And the same situation between the 9 and the 7. This 0 is also between significant digits. It's significant as well. So this number has 5 significant figures. Our next example has the 2 and the 8 that are automatically significant from rule number 1. Our new rule is applicable even though I've got a string of zeros. So all of these zeros are in between significant digits, which means that this number also has 5 significant figures. Rule number 3 is about zeros at the beginning of a number. All of the zeros in a number, such as 0 point something something something, all of these zeros are just placeholders. If we look at our first example, the 2, 4, and the 5, these numbers are not 0, so according to rule number 1, they are significant. The zeros in the front are not significant, so I'm going to put X's. And they're just placeholders. These zeros are all just pushing this 2 to the spot that it's supposed to be in this case, the thousandths place. If we look at our next example, the 1 is significant. The 3's are all significant, all of these because they're non-zero. Numbers at the beginning. These zeros are just pushing this 1 to the hundredths place, so they are placeholders. The 0 that's left here between the 1 and the 3, according to rule number 2, is significant because it's sandwiched. And so here I have 5 significant figures. Over here I have 3. One way you can do this and kind of determine whether you should bring the zeros with us is to use scientific notation. Now, scientific notation, we know from math class, has to be a number between 1 and 10 times 10 to some power. So in this case, I would have to move the decimal 2 places to have the number 1.0333 times 10 to the negative 2. And I didn't write the zeros that were placeholders when I changed to scientific notation. Scientific notation only uses significant digits in the first part of the times 10 number. So if you're ever asked how many significant digits are in this number, well, just count whatever's in front of the times 10, and that's how many there are. Our last example here, the 7, the 6, and the 9 are all significant, but all of the other zeros are in front of those numbers, so these are all still placeholders. rule number 4, is about zeros that are at the end of a number and after a decimal. So I'm going to do these out of the order that they're written here. I'm going to first look at 2.0. So the 2 would be significant because it's non-zero. The 0 here is a 0 at the end and after a decimal. So rule number 4 says if you're a 0 at the end and after a decimal, that you are significant. So this one has 2 significant digits. Now the last digit here, the last number, is 2.00. The 2 is automatic. The 0 in the middle, I don't have a rule that talks about zeros in the middle yet because I don't know if the last digit is significant. But our new rule says this is a significant digit because this is a 0 at the end of a number and after a decimal. So now the 0 that was in the middle is seen as significant because the last 0 was significant. So we created a point of reference to be able to use for this. And so this one has 3 significant figures. Now you might think 2.0 and 2.00 are the same, and mathematically they are, kind of. When we get to the rules for doing significant digits with math calculations, we're going to see that these numbers are not exactly the same. So the rest of these examples, 35.0, the 3 and the 5, automatic. That 0 at the end after a decimal, also good. The next one, 67.80000, 6, 7, and 8 are automatic. I don't know about these until I get to the end. Then at the end, this one is at the end and after a decimal. So now all these other zeros are in between significant digits. So this one has 7 significant digits. All right, the last example here has the 2, the 4, the 5, and the 6. All of these are significant. At the beginning here, between 2 and 4, that 0 is between 2 significant digits, so it's good. Between the 4 and the 5, between 2 significant figures, those are good. Between the 5 and the 6, also good. The 0 next to the 6, I don't know yet. But the 0 at the end has a rule. At the end, after a decimal, it's a 0, it's significant. So now this other 0 is in between. So this one looks like it is 9 significant digits. Rule number 5. This one is about numbers that are 1 or bigger that have a string of zeros and end in a 0. So it's probably easiest just to work out the examples for this one. What you will find here is that if you have a series of zeros and a 0 in the middle is significant, and everything up until then is significant, we would put a bar on top of the 0. If all of the zeros in our string of zeros are significant and it's at the end of the number, we put a decimal at the end. So here, the original number, our first one says 1,000. Now, oops, there we go. So now, if we have these zeros, they don't have any markings on them, so none of these are significant. So I'm going to find is that this is significant, but these are not. So this one has 1 significant figure, and if I were going to write this one in scientific notation, I would say 1 times 10 to the 3rd power. The second one, there's a bar on top of this first 0, so that means that the 1 is automatic, but everything up until the 0 with the bar on it is significant. Everything after is a placeholder. So this one has 2 significant digits. And so my answer would have to include that 0. So this would be 1.0 times 10 to the 3rd. On the next one, the 1 is good. The 0 is on the bar is on top of the second 0. So everything up until then is significant, and then not. And it's a placeholder. So 3. So this one would be 1.00 times 10 to the 3rd. And the last one, there's no bar anywhere, but there is this decimal at the end. That decimal at the end means that everything from the beginning all the way to the end is significant. Textbooks will normally use the scientific notation method to indicate very large numbers that have the significant digits that they're trying to express. It's very rare in a textbook to find the bar on top. People will write this because if they're writing out the expanded number, the shorthand is easier to put the bar on top of the last significant digit. I suspect textbooks have a difficult time with the font that would allow you to put a bar on top of a 0. So they instead use scientific notation pretty much exclusively from what I've seen. So addition and subtraction. We have a set of rules for addition and subtraction. It's the same set of rules whether you're adding or subtracting. So you take all of the numbers, you line them up at the decimal, and then you draw a vertical line that will cut off after the shortest piece after the decimal. So just like a chain is only as strong as its weakest link. In science, information is our chain, and the weakest piece of information is our weak link. So my answer can be no better than the worst thing that I'm using as a piece of information. Now, when I do the calculations, I get to keep everything to the left of the vertical line that we draw, and I use just the single digit beyond the line to see if the last digit I keep rounds up or stays the same. So here, I've got 42.3, 1.04, and 6.150654336. And I'm going to add these numbers together. So, my cutoff, let's see if I can change color for a second. My cutoff is here. And so when I work this out, I get 49.490654336. Okay, so my answer, so the line was drawn here because, oh, that didn't work the way I thought. So let's see. Okay, so anyway, the line is drawn because at the end of 42.3, I don't have any numbers. I go one place past the decimal. 1.04 goes 2 places past the decimal, and my last number goes lots of places past the decimal. So I have to use the next digit here, this 9, to determine whether this remains 49.4 or becomes 49.5. So the 9 rounds this up, so my final answer is 49.5. Now, all of these other digits after go away. You can't trust those. All right, another example. Here's 8.2, 221.22, and 0.028. And I'm going to add these numbers together. My line, once again, gets drawn after the 10th place. That's not necessarily always true, but in this case, it is. So here I get 229.448. Okay, so this time, the 4 determines whether this rounds up or down. And so this stays 229.4. A common mistake that I see people make is that they will try to take the 8 and say, oh, that would round up to a 5. Oh, and then that would round this up to a 5. But no, don't do that. It's a really common pitfall. Don't fall for it. The only number that's reliable is the one just after it. That's like your friend. After that, it gets sketchy. All right, here's another example. Okay, so these are all still adding together. The line is once again after the tens place on this one. So this is 20.0211. And so in this case, the 2 does not round the 0 up, so our answer just stays at 20.0. On this one, 15.91. On this one, our line is drawn at the decimal. So we have 20.0211. In this case, the 0 to the right of the vertical line is going to try to round the 0, and so we just end up with 20. However, this last 0, because it's to the left of this line, everything to the left of this line is significant and considered to be part of our answer. This has to have 20 with a point. So this is the final answer, is 20 with a point to show that that 0 is significant. That's a really commonly missed thing. And we have some subtraction here. 32.751 minus 6.03. And so we end up with, let's see, draw the line after the hundredths place. So we've got 26.721. And so my answer then is just 26.72. Multiplication and division also share a set of rules. So first we have to determine how many significant figures are in each number to be used. Then we perform the calculation, and then we have to round the number that we get for an answer to the smallest number of significant figures that we have. And the last two rules here we'll look at as we get to them. All right, so here we have 5.00 times 5.0. So 5.00, so the 5 is automatic. This is a 0 at the end after a decimal, and this one is sandwiched, so this one has 3 significant figures. This one, 5, and then the 0 at the end after a decimal, so this one has 2. So multiply these together, and pretty obviously you come up with 25. Now, I get to keep the smaller of these. So I get to keep this one, but not this. So my answer has to have 2 significant digits. So I can start the beginning, underline my digits, and since I get to keep 2, 25. So it's the answer we expect for 5 times 5. So this means that our measurements are good enough to generate what seems like a good answer. Now, 5.0 times 5.0. We know from the previous one that each of these has 2 significant figures. Because the 5 is good, the 0 is at the end after a decimal. We once again multiply this, we get 25. In this case, these numbers are the same, so that works out well for us. I get to underline the first 2, and my answer is still 25. So information is still looking to be pretty strong. We're getting answers that make sense. So now let's look at this one. So we've been saying so far these are 2 significant figures because 5 is good. The 0 is at the end after a decimal, so it's good. This time though, we have 5 by itself. So 5.0 times 5 tells me that I get to use this, but not that. So I've got 25 as an answer for 5 times 5. I'm only allowed to keep 1 significant digit, so I get to keep the 2. Now, I like to write the rounded answers directly underneath the original because it helps me keep decimals in the right place. So like here, a 5 rounds a 2 up to a 3, But I had 2 places in my answer, so I had to be able to, so that 2 is in the tens place. I need to be able to get back to the decimal. To do that, I need to add a 0. So this tells me that 25 is, 5 times 5 is 30. Well, that doesn't make any sense. And that's sort of the point of significant digits. What it tells me really is that the 5.00 was good, and just the 5 was bad, or at least not sufficiently precise to be useful for me. So what that really means is that I would need to go back and measure the whatever gave me just a 5 again, because it gave me an answer that didn't make any sense. And again, and that is the purpose of significant digits, is to save you from making bad mistakes and looking bad. So here, we've already seen 5.00, so we said that the 5 was good, the 0 at the end of a decimal, and now we've got one sandwiched in the middle, so that's 3 significant figures. The same thing is true over here. So my final answer has 3 significant digits. I know that this is 25, 5 times 5. But now, I've got this extra spot. So what I have to do now is to say I've got 25, and I've got to put another digit there. That digit can't change the numerical value of my answer. So I'm going to say 25.0. It went more places than the answer for 5 times 5 would give you on a calculator, but it tells me that I had an extra significant digit that had to be part of that. All right, and so let's do a division problem. So 9,354 has 4 significant figures. 554.9 has 4 significant figures. There aren't any zeros in this to try to figure out. So each of those are the same, so that looks pretty good. All right, so I work this out, and I come out with, on a calculator, 16.857091367.8. I'm only allowed to keep 4 significant digits, so I'm going to keep the first 4 that I come across. So I start at 1, so I come here. All right, I kept the first 4. The 7 rounds that 5 up to a 6. This is after, okay, so after the decimal, that's 7 rounds a 5 up to a 6. All the rest of that gets to be dropped. So this is 16.86. And after that, it all goes away. It all just crumbles and falls away. All right, so this one has 6.5808, so I know that all of my non-zero numbers are significant. So that 0 is in between significant digits, so it's significant too. So this one has 5 significant figures. Over here, 2, 3, and 4 are good, but there's nothing marking the 0 on this last bit, so that 0 is a placeholder. So this one actually only has 3 significant figures. So my answer should have 3, not 5. And when I work this in a calculator, I get 0.00281230769. So now, I need to work out what my final answer is. I'm going to switch colors again here. Okay, so I come past all of the zeros, and I get to keep the first 3. So my answer, and this 2 leaves the 1 the same, so 2, 8, 1. And so this is why I leave these underneath the original calculator answer. So now I've got to make sure that that 2 ends up in the thousandths place, so 0.00. I have to put 2 placeholders back in after the decimal. I prefer if you leave one, if you have to do a number like 0.00281, I would rather that you have the 0 in front. It's easier for me to tell that you actually intended for the decimal. If we do this on like virtually, you know, it's not as difficult to tell. But if you're doing this with me in person, sometimes I find not everybody makes clear decimal points. So my preference is that you put a 0 in front. All right, and one more. 14,752 has 5 significant figures. 7 has 1 significant figure. So if you so my answer gets to have 1 significant digit. If we work this out on a calculator, then we find that this will be 2,107.42857. Okay, I'm going to switch colors again. So I get to keep 1 digit, so I get to keep that first one. This rule is the one that students seem to have the most trouble with for rounding. So this one, I get to keep the 2. The 1 left the 2 a 2, but I need digits that are going to get me all the way back to the decimal place. So I need 3 extra digits. Those 3 digits are placeholders. They don't get any special markings, no lines on top, no decimal at the end. If I were going to write this in scientific notation, it would be 2 times 10 to the third. I don't get to keep any extra zeros. Everything after the 2 is just rounded. It's a placeholder. And so these are the rules for significant digits. I do have some practice work that I'll ask you guys to do. I'll attach some of that to your Schoology stuff, and that'll get us a good start on this. All right, and that's it for this.